So, hello everyone, my name is Sardar Ziyatkhanov. Today I'll explain the assignment. This is a YouTube video assignment from Calculus 2. So, let's start. Now I will show you the problem. The problem is f of x and y. Let's take this x and y. Sorry for ugly typing because of the trackpad. X square plus y square. Yes, this is our problem. So what should we do? We should find the critical points of this function. By the way, the condition also includes the x, y equals to 1. Yes. So let's start explanation. So first of all, we need to know what are the critical points. Critical points are the points where the gradient of the function is 0 or undefined. In our case, we have two real critical points, like it's -1 and -1 for x and y respectively. So the points, let's write the critical points, which are -1, -1, and 1, and also -1. Yes. So this is our critical points. This point, this is our critical point. This point satisfies both the constraint xy equals to 1 and has a gradient of 0 for the function, for this function exactly, for x squared plus y squared. So this is our first critical point. Let's mention it as first. So the second critical point for this function is the point 1 and 1. Just 1 and 1. Just 1 and 1 as a second point. As a second point, it's 1 and 1. What does this point means? This is a critical point. This is our second critical point, and 1 and 1 is similar to the first point. This point also satisfies the constraint xy equals to 1 and has a gradient of 0 for the function x squared plus y squared, f of x. So these are our critical points. Let's talk about the second partial derivatives. Also, we need, according to the problem, we need to find the second partial derivative to explain the nature of this function. So to determine the nature of these critical points, whether they are maxima or minima, or find the saddle points, we calculate the second partial derivatives. Here are the second partial derivatives that I will show you. So first of all, at -1, so -1 and 1, so -1 and -1, we see that the f of xx, like the second partial derivative for these points, is equal to 2, just 2. So what about the f of yy? Let's talk about this also. Fy and y equals to 2, also 2, as we found, as we see from this function. So but what about the fxy? Fxy just equal to -2, -2. This is for this critical point. Let's mention it like this. This is for first. Now I'm going to explain the second. What about the second critical point? Now we will talk about the 1 and 1. So for this critical point, we have fxx, like second partial derivative with respect to x, equal to 2. Fy and y, Fy and y also equals to 2. So what about the fx and y? Fxy second partial derivative with respect to x and y, it's also 2. The discriminant, so let's find the discriminant of the function. Like, let's find d. What is d? It's discriminant. What is this discriminant? Just calculated by the formula f x and x, like the second partial derivative with respect to x, multiplied by f second partial derivative of y, and minus f second partial derivative with respect to xy squared, just squared. Yes, this is our formula. But let's move forward and see what does it mean. For like also there should be the explanation for each critical point. Like, for example, for -1 and 1, we see that the discriminant for this critical point equals to 2 multiplied by 2 minus -2, -2, with the power of 2, like squared, and this equals to 4. This is our discriminant for this critical point. But what about the second critical point? The second critical point is 1 and 1. I'm sorry, there should be minus, like -1. 1 and 1. In this case, our discriminant equals to 2 multiplied by 2 minus 2 squared. Not negative 2, but 2 squared. This also equals to 4. So what is the results? The results is for both critical points we see that this discriminant D is positive and equal to 4. Since discriminant is greater than 0, this indicates that both -1 and -1 and 1 and 1, like both critical points, are at least candidate points for local max extrema. Additionally, both second partial derivative of x and partial derivative of y are positive at these points, which means that the function is curving upwards in both the x and y directions at these points. So let's talk about conclusion. For example, based on the second partial derivative test, we can conclude that both these critical points are local minima of the function under the constraint xy equals to 1. So after proving that, we see that these critical points like -1 and -1 and 1 and 1 are local minima of the function f of x and y equals to x squared plus y squared in the constraint xy equals to 1. Like in simple terms, these points represent the lowest points on the surface of the function within the region defined by the constraint xy and equals to 1. So thank you guys for watching this video. I hope that this video will help you. Thank you very much. Goodbye.